All right, should we get started? So just a reminder on the schedule, we'll have 2 lectures this week on theory and practice of lighting. And then the last 2 lectures will be spaced 1 week apart, again, just because of the availability of this room, ending on June 1st. Okay, I also need to apologize. I don't have the best photos ready for the landscape assignment, but I will on Wednesday. For sure. All right, so let's talk about light and reflection. And we'll start with mostly theory, but some photographic applications today. And then we'll talk about photographic lighting in depth on Wednesday. All right, so here's the outline for today. We'll talk about different ways to measure light. And this is a confusing topic because they differ only in the units, but they differ very fundamentally in their meanings, and we'll talk about all of them. And then we'll talk about light reflected off the surface and the different modes of reflection, and because some of them, again, have photographic implications as well. Okay, so first let's talk about radiometry versus photometry. So if you talk about radiometry, you're talking about the measure of light without considering the human. So it is the amount of light at all different wavelengths, whether or not, of the electromagnetic spectrum, whether or not we can see it. And so that's measured with a spectroradiometer, or just a radiometer to measure total power, and here are the units. So we'll talk about those units in a moment. However, photometry is the study if you include the limitations of the human visual system. In other words, we don't see infrared, we don't see ultraviolet, and so you would use a spectrophotometer to measure what we see, and a photometer to measure total power. So a photometer is nothing more than a light meter. So an ordinary photographic light meter is a photometer. It's already got programmed into it what we cannot see. And then the measurements are those, and we'll talk about those in a second. So the relationship between these two, then, you should already be able to intuit from the formulas that I talked about when I talked about color. So you've seen this formula before. The response of the human visual system, rho gamma beta, is the integrals of radiance times the rho function over the visible spectrum, comma, the gamma and the beta, times the spectrum of whatever source you're talking about. So we can also express then the total response as the sum of rho gamma beta, and then refactor this to be this function integrated over the spectrum, which is the radiance multiplied by this, where this is the sum of rho gamma beta. So this is luminance, and so this is radiance right here, and this function here, which is the sum of rho gamma beta, is called the luminous efficiency curve. So you just take rho gamma beta, there they are right there. So this is one of those weird representations where they're scaled up to the same, but that's not actually true. We're much less sensitive in the short wavelengths than in the medium or long wavelengths. But if you add those 3 curves, appropriately scaled so that S is much lower, you'll get this. And that is called the luminous efficiency curve of the human visual system. And there it is there, which is the sum of rho gamma beta. And so this is called luminance, and this is called radiance. So for the rest of today, we'll be talking mainly about luminance, although I'll quickly show you the radiance units as well. So everyone clear on the difference then between radiometry and photometry? Okay, so let's talk about the different amounts of light coming and going and what all that means. So the first quantity is the luminous intensity of a point light source. So if you assume it's a point, then what's useful to talk about is the amount of light leaving that per angle. And so that's lumens per steradian. So lumens is the photometric quantity. The radiometric quantity is watts per steradian, or joules per second per steradian. But we won't be talking about that any further. We'll just talk about the photometric quantity. So that's lumens per steradian. So what the heck is a steradian? So a steradian is a measure of solid angle, just as a radian is a measure of ordinary angle. And the definition is 1 steradian is the solid angle such that the area on the surface of a sphere, the area subtended by that solid angle when it hits the surface of a sphere is equal to the sphere's radius squared. So here it is geometrically. So the area of a sphere is 4 pi r squared. And 1 steradian is then r squared over 4 pi r squared, which is about 1/12. So that's the rule of thumb you can think about. A steradian is about 1/12 of the surface of the whole sphere. So if you want some intuitions for it, it's a circular aperture 65 degrees in diameter, in subtended diameter. Or if it's a square aperture, then it's 57 degrees on a side, subtended diameter relative to wherever the point light source is. Or if it's a street light, then it's a street light that's 10 feet high and casts a shadow 12.7 feet in diameter on the ground. Or we consider the amount of light falling in a circle 12.7 feet in diameter. So those are all measures of a steradian. All right, so we can also sometimes talk about the lumens per steradian. So 1 candela is defined as 1 lumen per steradian. And indeed, it is this guy's candle. And he had a very long description of exactly how you should make such a candle, what you should boil down, and how big the wick should be, and so on. Did the best job he could to standardize it in the 1700s. Okay, so that's 1 candela. Here's some examples. So a standard 100-watt light bulb with a luminous efficiency of 2.6%. That's terrible. The rest of the light given off, the rest of the radiation given off is mainly heat. The other 97% we don't see gives off 17 lumens per watt. So then you multiply that by 100 watts, that's 1700 lumens. And then you divide it by the number of steradians in the sphere, there's the 4 pi, and that gives you 140 candelas. So a 100-watt light bulb is like 140 candles sitting on the table bunched up together. We think of these as just point light sources. So it's 140 lumens through that steradian that I defined before. So that efficiency is kind of interesting, 17 lumens per watt. So if you just divide through by 0.026, if it were 100% efficient, it'd be 683 lumens per watt. So if it is 17.6, and if it were 100% efficient, it'd be 683 lumens per steradian. The compact fluorescent bulb is kind of in the middle, and it's usually about 75. So you can see what the relative efficiency of compact fluorescent is. It's not nearly 100% efficient, but it's a whole lot better than an incandescent light bulb. LEDs, interestingly enough, are not more efficient. They're just small and bright. They're actually less efficient.
In terms of heat versus light?
In terms of luminous efficiency, as I've defined it here, the amount that we see. It's less efficient than a compact fluorescent bulb. Not that much less, and a whole lot better than incandescent. Okay, so that's the luminous efficiency of a point light source. We can do photography by candlelight, but you need big pixels and a fast lens. So for this shot, which has 5 candles in it, this isn't that bad. It's a 15th of a second at ISO 400. But if you only had 1 candle illuminating her, then you would need ISO 2000, which begins to get a bit noisy, although not so bad on modern SLRs. Okay, so let's talk about the second measure of light. So the second measure is the luminance leaving an area source. So we talked about point sources, now we're talking about an area source. So the luminance leaving an area source is the power given off by the light per unit solid angle. You can see the solid angles here. Per unit area. So there's an area there. And there's this, so it's lumens per steradian per meter squared. Then there's this extra nasty little factor. For obscure reasons, they define it depending on the angle of observing. So if it's, say, 50 lumens per steradian meter squared straight on, but you're looking at it at this angle, then it falls off as cosine theta, and it would be about 70. It would be brighter. 70 lumens per steradian if you're looking at it from an angle. Now, in order for it to be actually brighter when you look at it from an angle, this has to be something that is giving out lumens per steradian uniformly. We don't see very many such light sources. Your cell phone does not give off light uniformly. It actually falls off as you go away from being perpendicular to it. But if we had a uniformly illuminating surface, then it would actually get brighter at a grazing angle because it's foreshortening, essentially. This is being bunched into something smaller. And so per unit area, it actually gets brighter.
So what would be an example?
What would be an example? I don't, that's a really good question. I'm trying to think if, so I will show you an example of a surface that reflects that way, but I'm not sure I can, well, let's see. So if I took this table and filled it with candles and then stood a fair long distance away so that it became sort of like an area light source, and then I looked straight at the candles, or I looked from an angle, that ought to get brighter. It's probably a technology example, but I'm not thinking of it now. Okay, so there is a number of other related units, and it's called a nit. And I know I could make a lot of lousy puns about nitpicking, but I won't. So 1 candela per meter squared is called a nit. And that therefore is 1 lumen per steradian per meter squared. So a computer display, which is, as I said, not really uniform, gives off 50 to 300 candelas per meter squared of the display surface. So remember I said that a 100-watt light bulb is about 140 candelas. So you can think of a large display screen, computer workstation screen, as being roughly the same as a 100-watt light bulb, but spread over the large screen. Okay. So we can also talk about, in those same units, the amount of light that arrives at a surface from someplace else. And it would come in like that. So we can talk about the lumens per steradian arriving at every point on the surface over some surface of some meter squared. And that's the same concept of luminance. And so these examples are from Minart's book. So this is a great book that I think I reference in the course schedule. Minart, Light and Color in the Open Air. It's sort of a gentleman Victorian scientist's take on optics effects in nature. But it's really very, very well done. And it's a good read. It's light enough to be bedtime reading, but he really gets into the details. And then it's been beautifully illustrated by a Finnish photographer after his death. It's a really spectacular book. Okay, so luminance arriving on a surface from a full overhead sun is 160,000 candelas, or candelas per centimeter squared. So if we have a piece of sidewalk here, it's going to be 160,000 lumens per steradian per meter squared. The luminance reflected by a diffuse white surface, let's say that sidewalk were 100% reflective, is only 1.6 candelas per centimeter squared, which is basically slightly more than a candle. So why this huge difference if the surface is 100% reflective? So here's where you really need to work these examples very carefully with respect to the geometry. So let me just work one example for you. I won't do this for everything I'm talking about today. But if we say that, so here's my hemisphere, and I've got a little patch of sidewalk here, and then I've got the sun up here. And so the sun actually subtends some angle in the sky. And so we can talk about the solid angle through which stuff appears. So the sun is about, 0.01% of the luminous hemisphere. It's, I know it in steradians, so 160,000 candelas per centimeter squared. Here, let's do lumens per steradian per centimeter squared times 0.00006 steradians. And so if you do that, you come out with about 10 lumens per centimeter squared. So that is the amount of light falling on the sidewalk. Now, if the sidewalk is a diffuse reflective, 100% reflective surface, that light, which is coming in through a fairly small solid angle, is then going to be reflected in all directions. So now you have to take that same 10 lumens per centimeter squared and then divide it through by the number of steradians in the hemisphere. So there are 4 pi steradians in the whole sphere, but there are only 2 pi in the hemisphere. Okay, so divided by 2 pi equals about 1.6 lumens per steradian centimeter squared, or candelas per centimeter squared. So you see where that comes from? So those are the kinds of calculations you have to do to get this stuff right. All right, so let's do a little bit more. If it's reflected by a black surface, it would be only 0.04 candelas per centimeter squared. And if it were reflected by the moon, it would be 0.3. So what color is the moon? See, so you can kind of work that out, right? So if it's 1.6 over 0.3 is about 40 to 1. And, let's do it. 1.6 over 0.04. And then 0.3 over 0.04 is, what, about 8? I have the exact numbers here. Yeah, it's about 7. Okay. All right, it's about 7. And so the ratio of this to this is about 6, right? So that means that the moon is about like an 18% gray card. So you can go to the moon and do your 18% gray card photography. It's about 18% reflective. It's got this special characteristics. It's retroreflective. We'll talk about that later. But just in terms of the total power reflected, it's like an 18% gray card. Okay, one more example that's useful for photography. The luminance arriving from a white cloud, fully lit by the sun, is 10 times the luminance of the blue sky. So again, you can think of from every piece of angle of the blue sky or of the cloud arriving per unit area on a surface, it's 10 times brighter. And so you ought to be able to test that yourself with a camera. Just point an SLR at a white cloud, point it at the blue sky, and you ought to see about 10, which is about 3 f-stops of difference. So expect you to all go out and test that out, except that there were great puffy clouds yesterday, but there are no clouds today. Okay. One more set of units, which is the, which I alluded to already here, which is the amount of light falling on a surface, regardless of where it's coming from and how it got there. And that's, excuse me, so that's just lumens per meter squared. So I already computed one in that, and that's called Illuminance. And the related unit is called lux. So this is lumens per, 1 lux is 1 lumen per meter squared. And of course the British have to have their own unit. They call it a foot candle. And it means a candela held 1 foot from a surface. British foot. So 1 foot candle is about 10 lux. And so architects will talk about things in terms of lux. So a couple of examples. The illuminance, meaning what falls on a surface from a bright star, is the illuminance that would fall on that same surface from a candle 900 meters away. So a single star does not illuminate a surface very well. or 1/800,000th of a lux. The illuminance from a full moon is about 1/4 of a lux, a little bit brighter than 1/4 of a lux. So here's a question. Let's work this one through. How far from a book should I hold a candle to make it match the illumination by the moon? Okay, so we know enough to work this through. But first of all, as I move the candle away from the book, how should the light fall off? So let's start with that. And
Assuming no reflection in the room around.
right, assuming nothing else going on in the room. And so you should already have an intuition for this. That's the 1/r² fall off. If I go out from d = 1 to d = 2, then it goes from 1 unit here to 4 units here. So for a point light source, the illuminance on a surface falls off as d². So we can actually do a little test to measure that. I've got a point light source here, and Arthur's going to blacken the room for me. And I've got an ordinary light meter. And so this is going to be sensing through this dome here, but since there's no other light to first approximation, we can just think about it as what is falling on a surface. And I need a volunteer. I think that. Oh, this?
Yeah.
Yeah, that might help. But it's, oh, okay, fine. All right. See if you can get up here without tripping over something. And you're going to be measuring distances. Why don't you stand behind? And so that should be 24 inches. And so I'm just going to turn on the light meter, and we're going to measure. And so it's reading off EV. So EV is like shutter speed, you can think of it. It's a measure of illuminance. Okay, so ready? All right, move that away. Let's make the measurement. And it says 6.6, 6.8. So there's some slop. All right, let's go out from 24 inches, go ahead, to 48 inches. Got it? All right. Watch this not work. So 4.7. So it went from 6.5 to about 4.5. This is like f-stops or shutters. It's like f-stops, the EV numbers. So each single number is a doubling, just like an f-stop. So if it went from 6.5 to 4.5, it was 2 f-stops, which is a factor of 4. So we went out a factor of 2 here and a factor of 4 in the intensity. Thank you. Okay. I'm going to need you again in a minute, but you can sit down. All right. So that is for a point light source. And now let's work through the example of the moon. So it starts off as a candle, which is about 10 lux. And so that's the candle at 1 foot. That's a British foot candle. And we need it to go down to the moon. So the moon is 0.25 lux. So the ratio there is about 43 to 1. So we need to decrease the illuminance by 43 to 1. So if it goes off as the square of the distance, then we need something like square root of 43, which is about 6.6. So if I was 1 foot away, I should move it to 6.6 feet away, and that will approximate the illuminance of the moon on a book. So I actually have done that, and let me show you what that looks like. If we assume this candle is giving out 1 candela of power, and I place the manuscript 1 foot away from it, then we can assume 1 British foot candle is falling on the manuscript. That's about 10 lux, and I can easily read the manuscript. If we assume that this is a point light source, and I move from 1 foot to 6 feet, then light should fall off by a factor of 36. So it should now be about 1/3 of a lux. Roughly moonlight. At this distance, I can't read the manuscript. The video probably isn't picking up much either. But if I bring up my cell phone and launch See in the Dark, after auto exposure and autofocus, it begins accumulating frames. And if we pause it, we can easily read the manuscript. That's what the cell phone sees. I showed you that app before when we talked about extreme photography. So it just happens that I was showing a book essentially at 1 foot and 6 feet, and so it's a perfect example for this. Okay.
Is it a separate app that could play that music based on seeing the notes?
Actually, if you look at it very closely, you realize that I played the wrong prelude for the music that's shown there, but never mind. Okay, so how does illuminance change with distance from an area light source? So it falls off as the square of the distance for a point light source. How about for an area light source? What do you think? So for an area light source, we could just take this, or any diffusely reflecting surface and pretend it's an area light source. So if I take a camera and I meter like this and then I double the distance, what do you expect to happen? Every photographer should know this. Should we do the experiment? All right, come back up here. All right, so let's go ahead and use this. It's going to be a little squirrely because there's some spotlights that are getting canceled. Oh, actually, you know what a good one is? Let's use this table. There will be less shadows, actually. So we'll do this horizontally. So we can go from like 1 foot to 2 feet. Okay. So what I'm going to do now is I'm going to switch. I'm going to turn this off, and I'm going to switch to measuring the amount of light on one small part of it by looking through a viewfinder. Okay. All right. So that's at 7.8. I go to 2 feet. Um, 8.1. Let's go to 3 feet. Do it again. So I've got it in a fairly tight zoom, so it should still just be seeing the table. 8.1. Basically doesn't change, does it? So why?
Point sources.
What's that?
You've got n squared point sources, and so even though each one is falling off as n squared, you're
Oh, all right. Well, let's diagram that out. Okay. So we've got we have a surface, so it's giving off light, and let's say I have a light meter or a camera lens. So I've got some aperture that's, say, this far away. And so it's capturing all the light going out through that area and then bringing it down to some sensor. All right, forget about that for a second. Okay, and this will, of course, subtend some angle, some solid angle in steradians, omega. So if this is d away, and I go 2d with the same lens, then the solid angle will be less. And if you just work out the geometry, that should be omega over 4. Drop as the square of the distance change. But if we think about how this thing is operating, let's say it is a 1 pixel camera, our photometer there, but we can think about the light falling on every pixel of a camera the same way. So there's also a field of view of that 1 pixel. So here's 1 pixel of a camera or the sensor on that photometer. And if we go from D to 2D, so we bring it back here, and we have that same field of view, so it's the same pixel, then look what happens. Instead of seeing H here, it's going to see 2H, or 4 times as much area. So we've got 4 times as much area, 1/4 as much solid angle. The two exactly cancel, and there is no change. So the illuminance due to an extended area source, let's say it's an infinitely extended area source, does not change as you change the distance from it. And you can go out and test that with your camera. Okay, so let's give some examples of illuminance that are useful for photography. So the luminance arriving on a surface from a full overhead sun is 300,000 times the luminance arriving on that same surface from the blue sky. But as we know, the sun occupies only a small part of the sky, so we could go through the same kind of calculation that I did before. 160,000 candelas from the sun, the fraction. I won't go through that calculation, but I think you see from the previous stuff I've done how you would go through a calculation like that. And if you did, and you knew this one number of the luminance of the blue sky, then you could work it through and figure out that the illuminance falling on a surface on a sunny day is 80% coming from the sun and 20% coming from the blue sky. So that's kind of interesting, because whether a surface sees the sun or sees just the blue sky is what's called a shadow. That's what we call shadows outdoors. So that says that a shadow outdoors is about 1/5 as bright as the lit area outdoors, which means that shadows outdoors are about 2.2 f-stops. So that seems fairly useful. You would think it'd be more, wouldn't you? And shadows seem dark, but it's really only about a little bit more than 2 f-stops of difference. We ought to be able to verify that empirically. Let's take here's a picture. We ought to be able to measure a pixel here and measure a pixel here, and there ought to be 2.2 doublings, or about a factor of 5, right? Not in a JPEG file. Ringer. That's right. You can't do that on a JPEG file. This was the giveaway here. You have to do it on a RAW file, because only that is linear with luminance. Okay? So I boosted this up a bit so you can see it on the slide. So if I were to do that here, in this particular case, I get about, 4 to 1. I don't get exactly 5 to 1. There are a lot of complicating factors. One complicating factor is that I'm kind of close to a wall, and so I'm blocking a little bit of the blue sky. And indeed, shadows are darker close to a wall. Those of you who ski know that if you're on a day when the sky is uniformly white, meaning it's cloudy, if you want to get a little bit of contrast so you can see the moguls, you ski right near the edge of the trail, where the forest trees are blocking half of the white sky, and that gives a little bit of contrast. Okay. So recap: radiometric versus photometric measures related by the luminous efficiency curve. And then we talked about the luminous intensity of a point source, the luminance per unit solid angle per unit area, and the illuminance accumulating on a surface, which is per unit area. The way to think about these, to get them straight, is think about the units, is to remember the units. And bright objects might be more luminous than dark objects, but you have to consider what fraction of the incoming hemisphere they cover. And then this thing about bright shadows. Any questions? Check the dory too. Quiet on the dory.
Is the right way to think about the drop-off of 1 over n squared just physically the number of photons packed into a unit area, the same number of photons, and as they're spreading out?
Yeah. Yeah, the way to think about the 1 over r squared fall off is just literally a conservation of energy. The same, if you have a point source and you're considering a certain solid angle, there are a certain number of photons that go out through that, and that can land on a small surface, or if you're twice as far away, it'll land on a surface that's 4 times as large, and there are no more photons. So it's just conservation of energy, exactly. Okay. Let's switch gears and talk about the reflection of light now. And we'll talk about diffuse, specular, we'll talk about goniometric diagrams, which are measures related to angle of reflectance of light, and even some more esoteric stuff like the Fresnel reflectance equations. Okay, so diffuse surface. A rough surface is the easiest way to think about it. Reflects light uniformly in all directions. So the appearance is independent of viewing direction. If it's perfectly so, it's called an ideal diffuse or a Lambertian surface. Now you have to be careful here. The luminance, the reflectance of a perfectly diffuse surface is actually falling off as the cosine of the angle. It is not sending out light equally in all directions. But that cosine fall off is canceled by our definition of luminance, which gets brighter as you go from this to this. Those two cosines cancel each other out. And so by appearance, it seems to be the same intensity from all directions. And so that's called a Lambertian surface. We can also talk about the total fraction of light reflected from a diffuse surface. So if it is diffuse, it's the same in all directions, and we can talk about how much light that is relative to what's falling on it. And it's, by convention, usually averaged across the visible spectrum. And so here are some numbers. So clouds have an albedo of 80%. Fresh snow is also 80%. What does that lead to? If clouds are 80% and fresh snow is 80%, there's something very important that that particular set of numbers means. What's that? Sunburn. Yeah, okay, sure. Where do Himalayan climbers get their worst sunburns? On the roof of their mouth. Because they can't put sunscreen there. But that's not what I meant. The fact that the numbers are exactly the same gives you more than sunburn. Can't see the horizon. That's right. So whiteouts and blizzards are because of that coincidence of numbers. All right, old snow, grass, soil, rivers, oceans. So when I talk about rivers and oceans, I'm not including the mirror reflection of the sun. So I assume we're not looking at the specular highlight. Florian?
So in the whiteout, the clouds are actually the source of light, right? And the fresh snow should reflect 80% of that. So there should still be a 20% difference.
Florian is saying because the clouds are the source and the snow is reflecting only 80% of that. I think you'd have to work out the geometry of it.
Yeah, the sun isn't between the clouds.
Yeah. Let me think about that one offline, because I'm pretty sure these numbers are correct there. And this is what Menard says, and I think it has to do with the geometry. Let's take that one offline.
Just another thought, though, isn't it the fact that you actually have a whole bunch of diffuse materials that are just scattering the light in every direction? So it has nothing really to do with the clouds per se, but rather the fact that you have surrounding you.
That's right, it's the geometry. I'm sure the geometry is the answer to this question, but I'd have to think about it offline. Yes, I agree with that. So one thing that's interesting to see just looking at this is that this ratio, 80% to 3%, it's not all that much. It's like 25 to 1. And this kind of reinforces the notion we've been talking about all through the course, that the reflectances or the colors of stuff don't vary by all that much. It's nothing next to the variation in the intensity of light. So sun versus moon is a huge difference, but white versus black is not that big a difference in terms of actual numbers of photons. Okay, reflection from shiny surfaces. So Bourguier did more than boil fat to make candles. He also came up with this idea of microfacets. And he said, if you assume that a surface is composed of what he called small asperities or microfacets. If it's fairly rough like that, then the light will be reflected in a variety of directions, and some of them may even be blocked. And so he called that would be a rough or a diffuse surface. If you began to polish that surface so that the asperities or the microfacets were a little bit shallower, then most of the light will be reflected sort of in the mirror direction, but there'll be some variation. And you can call that a specular or shiny surface. And then if you took it to extremes and all the asperities were perfectly polished out, then of course that's a mirror. And you can talk about statistical distributions or metrics of how much the surface normals, the orientations of these microfacets vary. And there are a lot of papers about that in the computer graphics literature. So diffuse reflections look the same regardless of viewing direction, so it doesn't matter which way you look. But a specular reflection moves when the observer moves, and you can see that in this example here, where the light source is fixed to the object, and we're just moving the observer, and that little shiny spot moves from one place to another. That is, of course, something you have to think about when you think about photography, but we all sort of do it kind of naturally. So while we're at it, let's just think a little bit about mirrors. So mirrors are fairly obvious. Maybe this is all completely obvious to you, but you do have to think about it when you're doing photography, that the focus distance of objects seen in mirrors is more than the distance from you to the mirror. It's as if the object were over here, whereas the reflection's being seen here, so that distance is larger. Another kind of maybe obvious thing about reflections is that they are not copies of the object itself. It kind of looks that way from this picture of Mitre Peak in New Zealand, but they're not copies, because if you look at the geometry, a direct view of that object would be from here to here, but when you see it in a mirror, it is as if you were standing here. So in a view where you'll see both the object and its reflection, the direct view would be this way. The virtual view, the reflected view would be this way. Obviously, they see different views of the object. You can't see that in Mitre Peak, but you can see it in many photographs. So the reflection shows the underside of the bridge. The direct view does not. So reflections of objects are not copies of the scenes. Here's one of my favorite illustrations of that, famous painting by Velázquez. And so who is Venus looking at in the mirror?
Painter.
The painter. She's not looking at herself, because if we see her, she must see us. So she's not looking at herself. Now, I suspect that Velázquez knew that, but maybe he figured the consumers of his painting would not know that. I don't know. All right. So there's a way that we can make these reflections a little bit more quantitative by talking about what's called a goniometric diagram. And so what a goniometric diagram means is just reflectance as a function of angle. And so here is a common way to draw these diagrams. There's the surface in cross-section. There's light arriving from some direction. And now the question is, how much light is given off in each direction? So if it's a diffuse surface, the amount of light is the same. And we'll draw the amount of light leaving in each direction as the length of that vector. And so if it is a diffuse surface and all these vectors are the same length, then we can draw an envelope over that. And that envelope is the goniometric diagram. So that's what a goniometric diagram is. So this is for a diffuse surface. So if we have a shiny surface, like the lower one there, it might be something like this. So first of all, we do care about where the light's coming from, so that has to be part of the diagram. And then maybe it only gives off a little bit of light diffusely, meaning in all directions. And so it's got this envelope here. And that's the diffuse component. But then it also is giving off light at the mirror direction, and quite a bit of it. And maybe a little bit at some directions that are kind of close to the mirror direction, but not exactly the mirror direction if it isn't a perfectly polished surface. And we can draw an envelope for that. Maybe it looks like this. And that's the specular component. And then the total amount of light given off in each direction would then be the sum of those two. And so we can make an envelope which is the sum of those vectors in each direction. Well, actually, it would sort of do this. So it'd be the sum of the vectors in each direction, and that would be the total reflectance. So you see the way that works? And that's called a goniometric diagram. You can also make goniometric diagrams for light sources. It just means some measure is a function of angle. We'll talk about that, but this is a goniometric reflectance diagram, so there's a shiny surface. All right, so everything I've done here in Flatland can also be done in 3 dimensions, and it looks like that. This is something a student put together at Stanford. And so we've got the light and the surface normal and the mirror direction. And so in the case of a shiny surface, there's the light coming in, there's the small diffuse ball, there's the specular component, and I think this purple shaded thing is showing the envelope that is both, so the total reflectance. And the peak will move as the light moves, which there's nothing to move here. But in this case, as you swing that light around, then the peak will move. That's what we think of as a shiny object. Okay, what unusual material property does this goniometric diagram depict? So it's kind of a funny looking bump there. Someone besides Florian. So what's that goniometric diagram doing? If it were diffuse, it'd just be a hemisphere, right?
More
So
at the sides and less directed out.
yeah, so that means if you were to look at the surface from the side, it would get brighter. But we're talking about reflectance of the surface. We're not talking about any light sources. So what kind of surface gets brighter when you look at it on edge? I mean, that would mean that if this were such a surface, if I get down here and look at it like this, it actually would be brighter. It's a very, very common material, very common surface that you've all seen. Yeah?
Metallic paint on a car.
That could be actually a metallic paint on a car. Depending on exactly what kind of paint it is. It might be kind of colored in a different way. So that's kind of a very special case where it's a composite surface with a lot of different stuff going on there. More common example, simpler example.
Maybe like linoleum floor type of thing.
Linoleum floor.
Laminate, you know, where it's sort of shiny.
That's the Fresnel effect. It's actually becoming specular. We'll talk about that a little bit later. That's a separate effect because that's actually, it's not uniform in all directions. That has a specular peak, the linoleum floor, right? Of course, I have to give the Dory a chance to answer a question like this. I'm not saying anything. All right, Florian.
No, I was wrong.
You were wrong. Okay.
Like a light pipe?
What?
Like a light pipe?
A light pipe. Oh, exotic optics again, huh? So, what's that? No, the moon is brighter in the same direction as the light source. So if this were the moon is retroreflective, and there would be a bump here right back in the direction of the light source. So how do you know if your house needs cleaning? Your wife tells you. Um, a dusty surface. How do you know if a surface is dusty? Get down there and look at it like this. See if you can see the dust, right? So an ideal scatterer would be perfectly horizontal. That's, of course, impossible from an energetics point of view, but so it falls off a little bit. But that appears brighter as you move to grazing angles. Artists have known this, and so here's something from the San Francisco Palace of the Legion of Honor, this particular painting, and if you zoom in on that one instrument, see the way it's a little bright at the top? It looks like it's dusty. Okay. Oh, let's try this one. How about that goniometric diagram? Brushed metal. Very good. So what's happening there is there's the incoming light source, and it should, what comes out here, so if this is the outgoing direction, the mirror direction, whatever, if it's a specular highlight like the kind that I've been talking about so far, it should be radially symmetric around that. And this one's not. It's kind of a lobe that is not radially symmetric around the mirror reflection direction. And so that's called anisotropic reflection. And so textured or brushed surfaces will have such a reflection. And it might, so we have to introduce some more angles if we're going to talk about that. And so here's a slightly more complicated diagram that shows the angle of declination from straight up. That's the thetas that we've been talking about. But it also introduces these azimuthal angles. So that means this angle. And those are the phis. And so a highlight may depend independently on the light phi direction and the viewer phi direction, the azimuthal angles. Like the horse. Oh, wait, we need a horse. And a horse? Yeah, okay. Or it may depend just on the difference between them, between the two azimuthal angles, as in something that's circularly symmetric, like the bottom of a frying pan. If I take that pan and I move it around like this, nothing changes. If I took the horse and did that, it would kick me, but other than that, it would change, because it has to do with the texture of the hairs on the horse. That's a Christmas tree ornament down there. Okay. We can also talk about if this is a bidirectional, this is called a bidirectional reflectance distribution function. So the function of the incoming declination and azimuthal angle and the outgoing declination and azimuthal angle. Has the units 1 over Steradian, never mind that. We can add more variables to that if we'd like. Talk about more complex surfaces. So two obvious variables to add are position. And then we need to actually add 4 variables and talk about the incoming point. So light strikes a surface at this point and leaves at a different point. And so that is what happens in subsurface scattering. If we are modeling it just as a function of what's going on the surface, and not actually modeling what goes on underneath, but simply characterizing it parametrically here, then we can think of it as arriving at one point and leaving at another point. And so you can make this 8-dimensional function called the bidirectional surface scattering reflection distribution function. Reflectance distribution function, the BSSRDF. And so that's very important in computer graphics. Because if you don't model it, then you don't get subsurface scattering. And so here's an example of that. There's no subsurface scattering here, and there is here. This arguably looks more human. And indeed, if typically a woman puts on too much base cosmetic, they may hide blemishes, but they will also kill subsurface scattering. And they'll look like this. So the importance of this in computer graphics gradually developed over about a decade and a half ago, and a variety of people started to model it. I built this camera rig at Stanford and started to measure it. And so there's a camera, and you can see the degrees of freedom here, and there's a lamp. And so you could use this to measure the BRDF, or if you had a projector here, if you had a projector instead of the lamp and then a camera, you could measure the BSSRDF as well. And so a variety of materials were brought into my lab and measured and then used to make images like that. And that, the paper by Henrik von Jensen won an Academy Award because it has been used a lot in special effects. I think the first movie was maybe Shrek, where it was used, and maybe that's the one that garnered the Academy Award for it. But if you look at their ears, you can clearly see that subsurface scattering. And just the fact that their faces look, well, natural for an avatar is because of subsurface scattering.
I remember Ratatouille was the first Pixar movie to do it, and it was really important because there's all this, like, the ears.
The ears of the mice, yeah.
They really look different.
Right.
Yeah, it's pointed out that all the masters of painting knew this because they would layer different colors of paint to get that effect.
The painters knew this absolutely for sure, yeah. Yep. Just by simple observation. Okay, so one more topic, the Fresnel equations. So I'm not going to go into these equations in detail. They're messy. These are the two different polarizations of light. Let me instead, where these are the angles. As I say, I'm not going to go into this. But let me enumerate for you some of the properties that arise because of the Fresnel equations. So it's basically a wave optics model rather than a microfacet-based model, rather than, in other words, a geometric optics model of how light interacts with a surface. And if you include those Fresnel equations, you get a variety of effects. So one effect you get is that metals, conductors, have a specular highlight that is the color of the metal. And so I think I have a shiny penny somewhere here, and its specular highlight is copper colored. Whereas a non-conductor, called a dielectric, has a specular highlight that is the color of the light source. So here's a book, happens to be The Introduction to Fourier Optics by Joseph Goodman, whose diffuse color is roughly the same as the penny, but whose specular highlight, meaning the shiny spots, are white, because it's a bunch of copper-colored particles embedded in some kind of plasticized material, and we're seeing the specular highlight off the surface of the plastic, and the plastic is a non-conductor. And so we see white highlights from this, and we see copper-colored highlights from this. So another, yeah, question?
So mirrors are silver surfaces?
Sorry?
Mirrors use silver, is that true?
Mirrors use, yeah, so that's correct. The reflective surface of a mirror is silver.
Do we see highlights as the color of?
Well, silver happens to have a specular highlight that is broad spectrum equal. So different metals will have different colored highlights. Copper happens to have a colored highlight. Not all metals necessarily do. So that's kind of an identity case in that case, silver. Good question. So another prediction of the Fresnel equations is that the specular highlight becomes the color of the light at grazing angles. So you can try this yourself later. If I take a penny and I see that the specular highlight is copper colored, and then I take it and get it right up at a grazing angle relative to the spotlight, which hurts my eyes, the specular highlight becomes white. So you can try that yourself. And even diffuse surfaces have a specular highlight at grazing angles. So there's your linoleum floor. If I just take an ordinary pad of paper and I run it up at a grazing angle, I begin to see a specular highlight. And it looks like it's a shiny surface. And that's Fresnel reflection. Fresnel, by the way, is very interesting because of Fresnel lenses. A very clever design he came up with in order to reduce the weight and size of lenses for lighthouses. And it's kind of clever the way that works if you've never seen a Fresnel lens. So the basic idea is you just take the surface of the lens and just displace it. So we'll take this part of it and put it over here, and then we'll take this part of it and put it over here. So you see the way that works? And so to first approximation, especially for a focus distance that's fairly far away, it's going to do the same thing that the original surface did. Again, for a surface that's far enough away. Otherwise, you'd have to change these angles a little bit. So it can focus light, but it is not nearly as big and heavy as the original lens. And so you could use it for large-scale applications like lighthouses. And the real purpose for this little digression is just so that I could show this gratuitous, beautiful photograph of Pigeon Point Lighthouse. And so the author ensures us that it's not actually Photoshopped, that this is, he was very, very lucky. They do this relighting, I think, once a year, and it happened to have just the right amount of fog and produce this spectacular photograph. Okay, and so here's a recap then. Diffuse, microfacets, specular, less variation in the microfacets, goniometric diagrams, which we can do in several dimensions. Total reflectance would be the sum of those two. And then there are lots of weird surfaces. Retroreflective is another one that we talked about. And then that's a 4-dimensional function. But we can also talk about 8-dimensional functions. We can even add more variables if we want, by the way. We could add polarization directions as well. We could add time for objects that have radian in them and glow after you illuminate them. So we could abstract a lot of stuff, a lot of physical phenomena, and put it in these kinds of functions. And then the Fresnel equations, which model some other. So any questions? See if there's anything on the dory. Okay, I'm going to end with a quiz. So you better ask questions first. Question.
You said that Fresnel lenses are not necessarily good for falling images. There are some Fresnel lenses that can be manufactured.
Yeah, Fresnel lenses are starting to be used actually in optics applications. That's no longer as true as it used to be.
What do they do to get rid of the circular?
What do they do to get rid of the circular effects? I think they just make I'm guessing they're just making the Fresnel facets very fine. But Florian probably has a better answer.
I think what you're talking about, though, is diffractive elements. They're not really Fresnel lenses, but they are, the way they're constructed, they look a little bit like Fresnel lenses. So they are based on diffraction.
Yeah, Florian is saying don't be careful not to confuse Fresnel lenses with diffractive elements, and that's true. But I've also begun to see some Fresnel lenses in optics. They're used a lot in light sources, like the lighthouse, but even fairly fine light sources or projectors, where the demand for the resolution is not quite as high. Okay, final quiz. So these vials represent progressive stages of pounding chunks of green glass into a fine powder. And so my colleague Gary Meyer just took pieces of green glass, put them in a towel and banged on them with a hammer. And every once in a while he would open it up and take out some pieces and put it in a vial and then put it back in the towel and keep pounding. So it's all the same green glass. But look what happens as the pieces get finer and finer. It begins to turn white. What's going on there? Wait, someone besides Florian? Yeah. Wow, very good. So as the surfaces, as the grains get smaller, there's more surface area. And so that's exactly right. And here's how to think about it. So if you have a couple of large chunks of glass like this, so light might reflect off the glass, and then it would just be the color of the light source. But more likely, it would go through the glass and preferentially be absorbed because it's green glass. It's absorbing the other colors. It becomes green when it exits. And then maybe eventually it'll then reflect off, okay? But if it's a bunch of very small facets, doesn't matter how small they are, they're very capable of reflecting light, and especially at grazing angles because of the Fresnel effects. And so the chances are that they'll, even if they went through one small grain, chances are they're not going to go through much, they're not going to change their color much by absorption, and they'll pretty soon hit something that will send the light back out. And so the Fresnel, the specular highlights and maybe the Fresnel highlights will dominate over the absorption of light more and more so as the grains get smaller. And that's exactly what happens here. Florian?
So, given that explanation, pretty much any substance, if you powder it finely, should become white, right? But that's not true.
Right. So Florian is saying that any substance, as you powder it more finely, should become white, and that's not true. Right. So this is a semi-transparent object, and it's preferentially absorbing. If this were opaque, then that wouldn't happen. It wouldn't matter what the grain size was. So I suspect that the powders that you're thinking of that are colored are opaque grains rather than pieces of glass. Is that's a conjecture from my part, but I think that that's true. So it is special that this happens to be glass. Okay, that's all I have for today. We'll pick up with photographic lighting on Wednesday.